This is Professor Alan Haungs, Physics 124, Ray Tracing Lab. It's software exercise number 3. What I did is I clicked on the download for the singlet finite conjugate thick lens. So you're going to be looking at a thick lens as opposed to an ideal lens. Singlet just means that it's just one, the lens is composed of just one component. Lenses may actually, one single lens may actually have multiple layers in it of different materials. Finite conjugate means that the light coming towards it is from a non-infinite distance, as opposed to a infinite conjugate. That would mean that the light coming toward it is from an infinite light source, infinitely far away, or something that seemingly is infinite, like a star or something like that, so that the rays of light are extremely parallel. So I clicked on that and it opened the software automatically. So first thing I do is I maximize this workspace window, and maybe it's not incredibly obvious what you're looking at here, so I'll just kind of move it around a little bit. It looks kind of like what you saw before with the single lens, right? I didn't have you do this, but I wish I had. So if you get it in this position and I click on the magnifier, if you were to look at this lens, it actually has some thickness. If you had done the same thing with the ideal lens, it would be as thin as a sheet of paper. So I'll go to this little trackball icon. You can see it's got a little bit of curvature to it. You can see the curvature on either side. This is where the right there, there's the origin in our arrangement. So everything that we can do using this as 0, 0. If I were to go up to the 3D view, and if I were to click on view towards, and this right here, the first one, now everything is oriented in such a fashion that make sure I did the right one here. Right there. Okay. Everything is oriented such that the Z direction starts at 0 here and then goes this away. So we're going to be building things after this, or putting light sources in front of it, or we can build either way, as long as we don't get confused with our pluses and our minuses. Now let's do a 3D view. We'll do a view all, so we'll look at everything again. There's everything. So I have 2 light sources. Now, I don't think you can see both light sources in your version because you have the student version. So we're going to have to fix one of them. So we're going to get you to fix one. So first of all, let's just open the geometry. The geometry says we have a focal plane and a singlet. Okay. Then we'll click on the optical sources. Click on the plus symbol. We have 2 point sources. So one is on axis, that's the red one. I don't know if you can see that clearly or not, but if I were to click on it, double click on this, here's all the details. It's got 500 random rays coming off of there with an emission cone of 5 degrees. Your software won't allow you to see that. Let's turn that down to 50 because you won't see that. It won't work on your software, but it'll work on mine. Okay. So we'll hit apply. So we just fixed the red. Okay, if you didn't fix it, you didn't do what I just said, you will not see anything when you do your retrace, your ray trace. Okay. Well, let's look at the green one. So the green one is off axis. So we'll just double click that. Now the other one was at 500 rays. This one's at 100. That'll be fine. And these are just various offsets and such. These numbers are actually, the distance numbers are in millimeters. It's assumed the system is in millimeters. So 0.66 millimeters off center. So these are all very small. These are actually very small lenses and things. Let's look at the actual lens itself, the size of it. If I double click on it, so it's what? It's got a 5.1 millimeter by 5.1 millimeter. Okay, the focal length is about 25 millimeters away. So probably from here to here is roughly 25 millimeters. Okay, so you can kind of see how all this works. So what I'm going to do is I will cancel this. I'll hit the ray trace again, and then I'll hit trace and render, and you'll see that again. It's just like you did with the other one. Well, first let's have a little fun. We'll just kind of roll it around a little bit just to see what it looks like in all the different angles. I mean, that's what it looks like. I'm just rolling it in space. Okay. Now let's look at the focal points, and I'll show you the difference between a real lens, and an ideal lens. Okay, so now I'll click on the magnifying glass, and we'll come in real close. And then I'll do it again, and we'll do it again, real close. That's as sharp as it gets. And what I want you to do is I want you to now use your snipping tool, and I want you to take a picture of that focal point. Take a picture of the red one and drop it on the Word document, and do the same thing for the green one. And that just proves to me that you're capable of getting to this point and doing these manipulations. You're able to change some parameters, because all this we'll be able to use later when we do the next lab. We'll drop some lenses in here and do something a little more practical than just getting familiar. So how would I do this? What if I wanted to back out? I could click on the ball. I can move it around a little bit. Okay. Then I would go up to 3D. I moved it around just to make sure that this will work. Sometimes it won't work unless you manipulate something and move it around. So if I say view all, now it backed off. Now I can go back, and I want to zoom in on the green. Look at the green. Now the reason why this happens, there's two reasons. Snell's law doesn't give you Snell's law is deficient in the sense that it's assuming that you're striking a ray against a perfectly flat surface, and therefore the angle is just a ray. It's just a pure beam of light, and its trajectory is just like a little bullet. In reality, Snell's law is problematic because all these real lenses, have a curvature to them, and that creates some of this effect is due to the fact that there's a slight curvature where any one ray goes through. The other reason why you can never get a perfect waist with a zero thickness waist is because there's something called a diffraction limit, and they might tell you about that in your lecture. I don't know. Essentially, the lens would have to have an infinitely wide surface to be able to generate to overcome the diffraction limit, to overcome a diffraction limit. So that means that this lens can't see anything smaller than this waist, and nor can it focus any smaller than this waist. So neither would it be useful for viewing objects that are super small or for super fine pinpointing. Which gets to, so make sure you do a capture of this and put it on your Word document that you're going to send to me. This is why this kind of software exists, because what happens is you can kind of do like what we did with the little ray tracing, and have a little fun with it, and build a system just by doing it that way. But what will happen is you'll have a blurry image. So you need to have actually for a good optical system, you would actually have several layers of lenses made of different materials, each of which will kind of help to massage that waist to be sharper and sharper. So that's why camera lenses may have so many different stacks of lenses, is to compensate for that. The other problem is that each wavelength of light actually has a different focal length. So in this system, you can actually decide what wavelength you're using, and you may find out that certain wavelengths have so right now we're using this wavelength. That would be 500 nanometers. That's the wavelength of this. No, it's not. It's the wavelength 500. Draw source red. Maybe what he did. Okay. we're simulating. This is the color he assigned to it, but it's a 500 nanometers of light, which would be roughly a green color, a greenish, a little bit turquoise color. So that's why it's so complicated. That's why you end up buying systems, software systems like this, so that you can play and play around until you get the sharpest focus that you want, based on different lenses that will help compensate for the different focal lengths of different colors, and then also to the fact that the little focus can't be so sharp. You can improve on it. So that's it. So basically, I just had you do 4 things. Right? What did I tell you to do? So I want you to do these 2 focal points, and I had you do the other focal point for the ideal, right? And then what else did I have you do? Let's see. What else did I have you do? Oh, and I had you also show me that you can drop a few items into the software. So what we'll do for next one is I may end up having some of these pre-made files for you ready for the next lab, and then you guys will kind of play around. I might have you drop a couple items on here yourself, see if you can make something work, and that's it. So this is just to get you familiarized, and you can play around. You can find different help. If you want to play around with this, there's all kinds of things to explore. And there's when you turn this thing on, the students version, you get a little help window that will encourage you to look at some of the tutorials if that interests you more. So I hope you have a lot of fun with this. Play around with it. You just drop stuff down, just do crazy things. Modify it, whatever. You can't save any of your work. So as soon as you turn off your program, it's gone. So that's the downside. So you want to start and you want to finish at the same time. Good luck, and give me a call if you have any problems. Okay? So this is an easy lab for you to do. Have a great day. Bye bye.